Magnetic field and shape of the conductor. Do you know about the junkyard crane that is used to lift heavy materials like a car? Though the junkyard crane operates with electricity, it is the magnetic effect of electric current that gives such a high strength to lift the car. The magnetic effect is withdrawn to drop the car. How do we get such a strong magnetic effect? How can we withdraw the magnetic effect suddenly? Let's find out. Electric current has the ability to create a magnetic field around the conductor and convert some materials into a magnet having a strong and variable magnetic field. The magnet that has a magnetic field produced by the flow of electric current passing through is called as electromagnet. The magnetic field of the electromagnets disappears when the current is stopped. This is what happens in a junkyard crane. When the electric supply is stopped, the magnetic effect is suddenly withdrawn, dropping the car down. The electromagnets are thus very convenient as they can be demagnetized instantaneously and they can produce an extremely strong magnetic field, as strong as to lift a car. What determines the strength and the pattern of the magnetic field produced by a current-carrying conductor? The amount of the current or its direction influences the strength and the pattern of the magnetic field produced by a current-carrying conductor. Can the shape of the conductor vary the strength of the magnetic field of a current-carrying conductor? When the current is passed through this current-carrying straight wire, magnetic field is produced around it. The pattern of the magnetic field lines is represented by concentric circles. Each point on the wire has such field lines around it. Let us check the direction of the magnetic field using the right-hand thumb rule. The right-hand thumb rule states that if we consider that the current-carrying straight conductor is held in a right hand such that the thumb points towards the direction of the current, then our fingers will wrap round the conductor in the direction of the field lines of the magnetic field. If we apply this rule for the current flowing in upward direction in a straight wire, the direction of the magnetic field lines around the wires will be from east to west. When the current passing through the current-carrying straight wire increases, the strength of the magnetic field increases. But the magnetic field becomes weaker and weaker when its distance from the current-carrying straight wire is increased. This is because the magnitude of the magnetic field produced at a given point due to current-carrying straight wire is directly proportional to the current passing through it and inversely proportional to its distance from the conductor. Thus, we have to increase the current and decrease the distance between the conductor and the magnetic field to get a stronger magnetic field. Now, we will bend the straight wire to form a circular coil with a single turn. what would be the pattern of magnetic field lines around the circular conductor? The circle consists of numerous individual points. When the current is passed through this circular coil, each point on the circle will produce a magnetic field around it. Let us consider the magnetic field formed at point B and point D. As we move away from the point B, the concentric circles would become larger and larger. When we reach at the center, the arcs of these concentric circles would appear as straight lines. In the same way, the magnetic field generated by the point D will also appear as a straight line at the center. The pattern of magnetic field lines for each point on the circular loop will appear as straight lines at the center of the loop. Presently, the circular coil we are using is having a single turn. We will add more number of turns to the wire. When the current is passed through it, the current flowing in each turn will create a magnetic field. Due to this collective increased current of the coil with more turns will have a stronger magnetic field than that of the coil with a single turn. In brief, adding more number of turns to the coil gives us a stronger magnetic field. As the direction of the magnetic field lines produced at each section of the loop is the same, each turn adds up to the strength of the magnetic field. This is how we get an extremely strong magnetic field in a current-carrying circular coil, as compared to that in a current-carrying straight wire. This shows that shape of the conductor significantly determines the strength of the magnetic field, along with the other factors like current passing through the conductor, distance from the conductor, and direction of the current.